Computational modeling of liquid crystalline properties. I'm going to present some review on this topic. Semi-empirical calculations. Using semi-empirical calculation for the estimation of liquid crystalline properties, the most important method is the molecular interaction. The molecular forces are divided into two categories: short-range force and long. Former are frequently called valence or chemical force, are significant when molecules come close enough so that their electron cloud have possibility to considerable overlap. Contribution of short-range forces to intermolecular potential varies exponentially. The separation are independent on the specific nature of the interaction being considered. On the other hand, long-range interaction varies as r to the power minus n at large value of r, where n is a positive integer. Thus, the long-range energy interaction between two molecules varies as r to the power minus 1 to r to the power 4. Classification of molecular force. It is classified into basic two groups, long and short. Long range is again divided into electrostatic, which is additive, inductive, which is non-additive, dispersion, which is again nearly additive, but both are repulsive. Then resonance energy is attractive but non-additive. And short range is type overlap, which is attractive but not additive. Electrostatic energy. The electrostatic energy of is the interaction energy of the permanent charge distribution. However, the separation between molecules is large as compared to their dimension. The multiple expansion of various components like charge dipole, dipole etc. may be conveniently implied. Electrostatic energy is given by the expression written over here, and polarization energy or induction energy arises from the polarization of one molecule by the charges of permanent electric movement of the other. These interactions are relatively smaller. The electrical expression for induction is given by this, where B and P prime are the polarizability of interacting molecules. P and R represents the dipole moment, molecular separation, and tau is function of quadratic quadrupole. Dispersive energy. The dispersive energy is a consequence of quantum mechanical nature of electron. This may be explained on the basis of average interaction on an instantaneous electrical movement on a molecule brought about by fluctuation in electrical charge distribution, and the moment introduced by it on the interacting molecule. At distances that are large in comparison with the size of the interacting system, the dispersive energy varies as the inverse of sixth power of distance. However, the dispersive forces are always attractive for molecule ground state because of the inverse sixth power dependence. This forces vanishes very rapidly with increasing distances and are usually significant between nearest neighboring molecule only. London presented a sound description of dispersive forces on the basis of the second-order quantum mechanical perturbation theory and developed a useful expression for their appropriate evaluation. Resonance energy. The resonance energy is the additional energy that results when the degeneracy is removed by interaction. The degeneracy may arises because one of the interacting molecule is itself in degenerate state, as is the case of hydrogen atom in excited state interacting with an ion or a polar molecule. However, during any particular collision process, the resonance energy may be either attractive or repulsive depending upon the quantum number describing the state of pair. Resonance energy has an important role in determining width of the rotational line in the pure rotation and rotation vibrational spectra of smaller gaseous molecules. Finally, magnetic resonance interaction also exist with the molecule and they play a finite though minor role. These interactions are so big as compared to the corresponding electrical interaction that one can frequently ignore. Theory of long-range intermolecular interaction. This is often known as Rayleigh-Schrödinger perturbation theory, has been examined by a number of authors over a number of years. Here we present a theory according to Buckingham. The induction energy is therefore the sum of two parts. Induction energy is equal to e to the power a induction and e to the power b induction, where e to the power a induction e, which gives us dispersion energy summation of some function given here. Semi-empirical potential. Different forms of intermolecular potential functions have been listed in literature. These have been used to calculate various properties. In choosing any particular form of potential function, one has to consider two factors: degree of realism desired and the numerical difficulties associated with the manipulation of function. Here the first function shows the rigid sphere and second is the point center of the repulsion. Square wave potential is represented in this figure. Southern model is also represented here, which is a modified square wave potential. Then comes the Lennartzian potential, which is further modified by the Buckingham. The expression for well-known Lennartzian potential is Vr is equal to 4 epsilon sigma by r to the power 12 minus sigma by r to the power 6, which is also known as 612 potential. The computational scheme for intermolecular interaction. A detailed computation have been provided by Cleveridge suitable for evaluation of interaction energy of large interacting system with whatever complexity. The simplified formula described by Curry as follows. Total intermolecular interaction energy between any two molecules may be expressed as sum of Various computing term accordingly, E total is equal to E electrical plus E induction plus E dispersion plus E repulsion. The real E dispersion and represent the electrostatic, induction, dispersion, and repulsion components respectively. Electrostatic energy. The molecular charge distribution is expressed as the set of atomic charge Q, referred to as monopoles, and the atomic dipoles M, which can be obtained by using any all-valence molecular orbital method. According to multi-centered multipole expansion method, the electrostatic energy may be expressed as the sum of individual terms between atomic multipole as under electrostatic is equal to EQQ plus EQM plus EMM plus so on, where EQQ, EQM, and EMM etc. are the dipole terms respectively. In general, the first three terms have been found to be adequate for the most of the molecular system. Polarization energy. The polarization energy, sometimes called as the induction energy of a molecule, is obtained as sum of induced polarization for various bonds involved. E induction for a molecule is equal to C minus 1 by 2 summation over U rho epsilon sigma is equal dispersive and short range repulsion energy. These two terms have been traditionally considered together, as has been done in semi-empirical derivation of the Leonard or the Buckingham type cases. As mentioned earlier, Pitofsky adopted six exponential potential and later on modified the parameter to suit all type of molecular system, and which is given by the expression. Computation of interaction energy at various configuration. Here first shows the six phases of the molecule, and for interaction they are termed as stacking side A, side B, plane side A, plane side B, or in plane interaction side A, side B, and terminal interaction side A, side B, which is explored like this. This is the stacking example of stacking interaction. Then this is the when the molecules are interacted along a y-axis, then it is in plane interaction. When the molecule is interacted along x-axis, it is termed as terminal interaction. Here are some calculations showing the intermolecular interaction in liquid crystal with the same formula. E total is equal to electrostatic plus E polarization plus dispersion plus repulsion. This is the case of biphenyl 4-carboxylic acid, and here are the energy values for stacking interaction. And one can see that dispersion energy has major contribution to the total energy in the stacking. Similar is the case for the in plane interaction, planar interaction, and even in the terminal interaction. Another example is PN propoxybenzoic acid. Here we can again see the major energy comes from the dispersion, and the repulsion has also its own contribution which reflect in the total energy. The characterization of mesogen, the following aspects were found to be useful. First, the pair potential in mesogens generally possess orientational specificity toward 0 or 180-degree intermolecular orientation. The relative value of interaction energy in state, planar, and terminal complexes are also very important, since if these values are comparable, it is more likely that the molecule will directly go into solid form from the liquid state. If any two of the above mentioned energy are comparable and possess tendency of sheet formation, cinematogenic character is more probable. Even of odd effect in homologous series roll up an isotropic pair potential. For the even odd effect, the role of terminal substitution, that is alkyl chain, has significant. All nematic crystal molecules contain at least one terminal alkyl chain. Plot of alkyl chain length versus liquid crystal phase transition temperature for two triple system is shown here. This is for the cyno system, that is 4 trans 4 N alkyl cyclohexane benzonitrile, and this N represents the number of alkyl chain, and this is the phase transition temperature, and one can see that as number increases increases, it goes into even and odd direction simultaneously. Another example is 4 and alkyl 4 cyanobiphenyl. Here again, as the N increases, initially the transition temperature decreases, but when it crosses the N is equal to 5, it shows the alteration in the phase transition, okay, up to the 9, and from 9 it become phase transition temperature become. This alteration in the phase transition temperature is an even odd effect in homologous series. The normal alteration of transition temperature can be explained by odd carbon atom alkyl chain having the terminal CS3, which extend the long molecular axis, whereas in the even number of carbon chain, the terminal CS3 tends to lie off the axis. One can see from here that when it is 3, it is in the same axis, but the moment it becomes 4, it goes off the axis. The homologous series containing R, OR, COR, where R is an alkyl, as terminal group of the following regularity become apparent. The terminal CS3 in alkyl chain with an odd number of carbon chain atom lies along the long molecular axis. The homologous series containing ROR and COOR as a terminal group, the following irregularity become apparent. The transition temperature of pneumatics decreases with increasing transition temperature of pneumatic decreases with a fairly distinct alteration. The amplitude of alteration also being reduced with increasing the chain length. If the first member of homologous series are already relatively long, the alteration is less apparent. Schematics are rarer with short chain but become more common with longer chain. The plot of transition temperature of schematics and their transition point to the pneumatic usually reaches a maximum to moderate chain length and decreases gradually with further elongation of chain. The plot normally shows no distinct even odd effect for schematics. An attempt has been made to correlate this energy with transition temperature, hence to understand the even odd effect at molecular level. The molecular chosen is the PN alkoxybenzoic acid, where the one side of this has polar group, hydroxyl polar group OH, and another side is alkyl chain, and the side defined as side A, side B for stacking, CD for in-plane terminal, E and F for the terminal. Stacking interaction. Stacking interaction is divided into two parts, part side A and side B. For this studies out of two molecules, one molecule is kept fixed. Another molecule is allowed to move and rotate or orient itself. So when another molecule is have a interaction in x direction for one side of it, then it is side A. And when it is in the another side of the molecular system, a transition along z direction, then it is side B. And lowest energy configuration energy is plotted. Figures below reveal that dominant component of total energy is the dispersive energy. The contribution of polarization energy and electrostatic energy is negligible. Since stacking side A covers all the components, the benzene ring and the carboxyl group and alkoxy group and total binding energy is almost constant with the homologous number, which suggests that there is no role of long alkyl chain in stacking interaction of side A. Therefore, no odd even effect has been observed as evidence from this figure. But that is not the case for the side B. In the stacking interaction of side B, the role of alkyl chain is well distinct. As the chain is elongated from 2 to 3 and 4 to 5, the intermolecular separation increases. Since the odd alkyl terminal lies off the molecular axis, the extension of alkyl chain from 1 to 2, 3 to 4, and 5 to 6 increases one bond parallel to the molecular axis. So, in such case, interaction energy decreases due to increase the number of atoms at same intermolecular separation, and one can see the pronounced odd even effect in the side chain. Now, in plane terminal, that is side C interaction, it is clear that from this figure that repulsion energy show a slight alteration with homologous series. But the dispersive energy show a compensatory effect. The dispersion energy has major contribution to total energy. The total energy does not show the alteration with the homologous series. An interaction inside B. Again, we see that electrostatic interaction has some alteration, but the dispersive energy also having the compensatory effect of the electrostatic part, as the total energy does not show the any or even effect or alteration in the energy. In terminal, inside a E interaction, the presence of carbonyl group at one end show the tendency of forming dimer with double hydrogen bonding. It is also evidence from figure that interaction energy is almost constant with homologue number. Here the major contribution of total energy comes from electrostatic energy. This shows that the molecules have a strong tendency to form dimer by hydrogen bond. In terminal side F, interaction between alkyl chain in the molecule have the band structure. The terminal interaction decreases with increase in the homologous number from 3 and onward. A minor alteration of energy between homologue number 1 to 3 is due to less pronounced band structure. Here also the major contribution in total energy comes from dispersion energy, while the repulsion energy show compensatory effect. When we come to the total energy, the total stacking interaction side plus side with homologous number shows distinct or even effect. As a result, total interaction energy also shows the same effect. The amplitude of alteration in interaction energy decreases with increase in homologue number. The total number reported here corresponds to the association energy with the first neighbor of all atoms. This refers only to a local ordering energy. Quantum mechanical calculation. The problem with semi-empirical method is that it can only provide the rough estimation of other properties such as polarizability, dielectric constant, and other properties of liquid. Calculation based on quantum mechanical method or density functional theory can provide estimation of liquid. A brief review of such calculation are there are two most important DFT method, hybrid DFT method. One is V3 leap, another is M062X. Here are the comparison between these. The V3 leap approach belongs to the hybrid approximation for the exchange hybrid correlation function. It is hybrid functional with for 15% artifact exchange. It, it is good performer for geometry optimization. M062X functional is based on the meta-GGA approximation because this includes all terms that depend on the kinetic energy, density, and are all based on the flexible functional form parameterization on the high-quality benchmark database. It is global hybrid functional with 54% artifact exchange. It is good performer for the main group thermochemistry, kinetics, and non-covalent interaction. The three parameters defining B3 have been taken without modification from Beck's original fitting of the analog B3P W91 functional to a set of atomization energy, ionization potential, proton affinity, and total atomic energy. Actually, in this method, fitting parameter obtained from the ab initio calculation. M062X belongs to M06 class functional, which relies on the spin density, cities, spin density gradient, and spin kinetic energy density. And for the non-local hybrid functional, artifact exchange M062X is a hybrid meta-functional, has excellent performance for the main group chemistry. It is quite accurate for the predicting the valence and the Rydberg electronic excitation energy, including dispersion, correlation, correction, provided the excellent result for the aromatic stacking interaction. General M06 family is constructed with the empirical fitting of other parameters. Optical property effect of electric field on the polarizability. Effect of electric field. Any LC molecule possesses permanent electric dipole. Under an electric field, the molecule tends to rotate until the positive and negative end line up with the electrical field as shown in this figure. This is another example. The positive tends to one direction, negative tends to another end. If it is like this, then positive will go in one direction, negative will be go in one direction. This is the waveform of the our presentation. Ordinary wave. This is for example of ordinary wave, and this is for the extraordinary wave when field is perpendicular to the axis, and ordinary wave when field is parallel to the axis. Polarizability can be considered as parameter for exploiting effect of electric field because the value of polarization depends on the electric. Forces like dispersion and interaction energy within molecule and material are affected by polarizability. In liquid crystal, the molecular polarizability and its anisotropy are important inherent molecular property because it represents the dielectric anisotropy of liquid crystal molecule and intermolecule interaction energy depend on them. This is the given formula. The system chosen for the studies basically have two type of liquid crystal. Two-ring system without linker, that is R2WL. Three-ring system with alkyl linker is shortened as R3EL. Here are the name of the molecules which are studied here. For the two-ring System without alkyl chain for first molecule, 4-cyano-4 prime pentyl biphenyl. This is the product of polarization against the electric field. As the electric field increases after a limit, polarizability has a constant value till a particular range and then it falls down. Similar is the case for the also for 2-cyano-5 4 pentyl phenyl pyridine. Another case is 2,4-cyano-phenyl 5 pentyl pyrimidine and 5-cyano-2,4 pentyl phenyl pyrimidine. In all the cases, we actually saw that polarizability increases to a certain level and then it goes constant for a particular range of electrical field. This clearly signifies that the optical property of this type of molecule will be good enough for this particular range of the electrical field. Similar the case we found for 3-ring alkyl with alkyl linker. There are 4 examples that 1-phenyl 4,2, 1s4r4, methyl cyclohexyl, benzene, and all those. As we see, the system is changed, but behavior polarizability with electric field it does not change. And second interesting thing is that as the polarizability increases, homo-LUMO gap decreases with the electric field. Analysis of molecular charge distribution of respective atom of these molecules revealed that conjugation effect due to increasing electric field. One can see over it. These are another set of molecular charge distribution for different type of molecules. Inference: the variation of homology gap and polarity with electric field bear a common phenomenon. That is, there are two regions, upper and lower, at which polarizability remains almost stable, and a suitor point to these two regions. Homology gap decreases in a uniform manner and then get stabilized. Polarizability as well as homology gap remain stable within a particular range of electric field and around a certain level. Polarizability shoot up above a point due to conjugation. As the electric field is increased gradually, the polarizability attained stability due to availability of large number of mobile electrons. Further availability of mobile electrons due to conjugation also results in decreasing of separation. Polarizability suffer a steep fall beyond a certain value of applied electric field due to irregular distribution of electrons. The possible reason is that the increase in magnitude of field results in conjugation effect whereby electrons prefer to delocalize instead of localized. Presence of more electronegative nitrogen makes derivative less polarizable by countering the effect of cyano group as the higher field is required to reach the suitability region. Substitution of hydrogen with different groups such as fluorine, chlorine or cyano affect molecular length as well as the charge distribution, which have direct effect on the polarizability. Now I am going to show some results on the bireferences effect of electric field on bireferences. Optical anisotropy. The Lorentz equation correlating the refractive index of an isotropic medium with molecular probability at optical frequency was modified by considering that internal field in a liquid crystal is equal in all directions, thus producing a semi-empirical equation that correlates macroscopic refractive index with the microscopic molecular polarizability for anisotropic media. This is given by the equation 1, where N1, Ne and N0 is the refractive indices for extraordinary and ordinary rays. Capital N is the number of molecules per unit volume, and N square is the average of refractive index induced defined as, which is given by the equation 2, and by substituting 2 into 1, the separating NE, we get the following expression. Among the liquid crystal developed so far, most of them have their refractive indexes around 1.45 to 1.8. This means the second term, the square root is greater than 1 but less than 0.24. Expansion of equation 3 into power series requires the modification as given by. Therefore, in last, we get the change in refractive index and its inverse, which is represented by equation 7. If we keep the center of molecule fixed and move the molecule in all directions, it will be subscribed a sphere having diameter equal to the long molecular axis of the molecule. Thus, we have n is equal to 1 by 4, 1 by 4 third of pi r cube. That is the one molecule in volume of a sphere having r radius. Putting this value in equation 8, we get the one inverse of change in refractive index, and the Gaussian 09 gives result in atomic units. So we need to convert the polarity into electrostatic unit, that is 1 centimeter equal to 6.748 into 10 to the power 24 AU for polarizability, and 1 AU is equal to 1 by 6.748 into 10 to the power 24. Putting this value, we have the change in refractive, and thus we can use equation 10 to determining the references for the values of polarization provided by Gaussian line for desired pneumatic. These are the names of the molecule with their molecular length, which are studied for the bireferences. That is 16 in total. Bireferences are calculated at the field where the polarizability along x-axis considering as externally in maximum in stability region and considering polarizability along z-axis at the corresponding field as ordinary polarizability, and we calculated here in table we can see the experimental value theoretical using V3 lead. In first case, this is deviation is 40% for V3 lead and 6% for M02X. In second case, V3 lead has deviation 32%, but M06 to X has variation of 0.3%. Similar is the case of the third. Here, the B3 leaf estimates the 4%, whereas M06 to X represent the 31%. And similar is the case. So one can see that molecular geometry devises which method is more suitable for the calculation of bireferences. One can say a set of molecule and see the similar case. Different molecular structure can be studied by different method, and that is giving a rough parameter. This review gives the rough parameter for which type of molecular system, which method is good for presentation and calculation. The estimated reference ranges for the molecule 3, 4, 7, 8 using value of polarity obtained for B file are good agreement with the experimental data, and molecule 7 gets minimum deviation of 0.6. Estimated by references for molecule 1, 2, 5, 6, 10, 16 using values of polarizability obtained from the M02X are agreement with experimental data. Molecule gives minimum deviation of 0.3%. Inference. Both molecule 5, 6 have pentyl chain, and for both molecule the estimated value for references using M02X are in good experiment. On increasing alkyl chain, as in case of 3, 4, 8, 9, the estimated result using B3 have a good agreement with the experimental data. For molecule 7, having peptide chain, B3 values give the better result for estimated by references, but for substitution of halogen in the benzene ring, molecule 11, the estimated references using M062X value is close to 1. For all the other molecules without any linker, 1 and 2 have two benzene rings, molecule 12 and 16 have 16 have two benzene and one cyclohexane ring. The estimated by references using M062X value gave good agreement with the experimental data. Now, let's talk about the bireferences, few more things. Variation of bireferences with homologous series. The birefringence decreases with increase in carbon atom of the alkyl chain. The CS asymmetric stretching of correspond to IR absorbance in the benzene ring and improvement of odd for the odd number and fall for the even number of alkyl chain. Tense Cv liquid crystal is even member of NCb series. The higher absorption in increasing instead of decreasing the tense CVLC, that is the region for sharply reducing bireferences. One can see here the alteration of bireferences by with the variation of alkyl chain studied with two methods. The order parameter. Here is symmetric stretching of benzene ring at a frequency of 1532 centimeter per centimeter is showing higher absorption for odd number and lower IR absorption for even number of alkyl chain. CC symmetric scissoring in benzene ring is responsible for the molecular phases at the frequency of 2266 centimeter per centimeter. The CN atom stretching correspond to absorbance is continual increases, which is accountable for the increase in the order parameter. Here are we can show the plot of the order parameter with increase and homologous series using two methods B3 and M062. Refractive index. The CH atom asymmetric stretching in alkyl chain is continuously increasing. In the 10 CBLC, the refractive index abruptly increases because the CH is asymmetric stretching correspond to the higher absorption is growing instead of decreasing in the benzene ring. The refractive index does not express any even odd effect. It is continual increases. The H atom rocking in the both benzene ring correspond to higher frequency 1532 per centimeter is increases only in NLC, which is responsible for abruptly increasing the refractive index. The higher spectrum of 10 CVLC also indicate the absorption due to H atom locking to the both ring. Molecular spectroscopy and adverse optical property of HBT liquid crystal molecule. All the optical properties were computed using by applying the electric field in all the direction as shown in this, where X axis represents the molecular axis. Order parameter. The polarity ordinary polarity increases and extraordinary decreases under the influence of an external electric field. The positive order parameter for SBT liquid crystal is 0.68 in the present work. The positive parameter of 0.67. The theoretical prediction is very accurate with the experimental impedance. The maximum order parameter for HBT-LC liquid LC is 0.677 and minimum of minus 0.3865. The Y references. The Y references in the nematic phase exhibit between zero point 0.2 to zero point 0.1. The present work also indicates the Y references of nematic phase is 0.1119. The ordinary polarizability increases and extraordinary polarizability decreases with an impact of temperature. The present work indicates the adverse and negative bireferences of SBT-LC molecule. The maximum bireferences of SBT-LC is 1.1119 and the minimum is minus 0.0814. Character angle and magic angle. The magic angle for liquid crystal is 54.7. The present work also indicates the magic angle of SBT-LC is 54.73. The maximum range of director angle is 74.03. The minimum range is 27.56. The director angle is stable for the nematic and sematic phases. Higher spectroscopy of SBT liquid crystal. The CO stretching express the maximum absorption because the oxygen atom transfer the exchange of benzene ring during the intermolecular interaction. An oxygen atom transfer the proton to the nitrogen atom during the intermolecular interaction, which is responsible for the maximum transmittance of the molecule. Vibrational mode of HBT liquid crystal. It is divided into two columns. One is frequency per centimeter and mode of vibration. 565, which is CH bagging in benzene. 845, out of plane bagging of hydrogen atom. 976, OC stretching, carbon atom of alkyl chain. 1178, in plane scissoring of the CH atom. 1232, OC stretching, carbon atom of the benzene ring. 1342, CC stretching in benzene. 1426, CH out of plane waving. 1539, CH in plane scissoring in benzene. 1631, CN stretching in plane scissoring of CH atom. 3030, CH symmetric stretching in alkaline chain. 3092, CH asymmetric stretching in the alkyl chain. 3191, CH asymmetric stretching in Even odd effect of 7OM liquid crystal compound. This is studied under the effect of electric field. As I told you earlier, the long molecular axis is considered as x-axis. Electric field is applied in all the direction, that is the plane parallel to the x-axis, parallel to the y-axis, and parallel to the order parameter. The order parameter of 7OM series sharply decreases with 7O6 molecule exhibited by both method B3 and M062X. Because the bond orientation order break rotational symmetry and exhibit symmetric F phase. Experimentally reported, the order parameter of 701 exists between 0.42 to 0.63. In present work, the order parameter for 701 is 0.41, which is indicated by the B3 method. By references. By experimentally calculated by references for 702, 703 is zero point 0.1 and 12 and zero point 0.1. In present work, the by references for 702 and 703 is 0.120 and 0.11. Experimentally calculated by references for 704 and existing between zero point 0.1 to 0.15. In present work by references for 704 is zero point 0.1. The 0.706 liquid crystal molecule decreases the by references because the bond orientational order break rotational symmetry and exhibit symmetric F phase. The F06 and F08 F did not have a having a nematic phase, which is the region for the salt element of the birefringence indicated by the method B3 leaf. Dipole moment. The dipole moment perfectly expresses the even-odd effect with increasing length of alkyl chain of the 7OM compound series. In 7OM compound series, the dipole moment increases for the odd carbon number 357 of the alkyl chain and exhibit odd even effect slightly. The dipole moment decreases, the alkyl chain increases. Still, after 707 liquid crystal molecule, the even-odd effect does not observe. Still, the dipole moment decreases continuously as the length of alkyl chain. So, refractive indexing. The even odd even effect does not observe in the refractive index calculated by the B3 method, while a little bit odd even effect observed in the refractive index calculated by the M062X method. The M062X method expresses a high amount of refractive index as compared to the B3 method. Experimentally reported refractive index of 704 is 1.57. However, the theoretical prediction of 704 is 1.57, which is indicated by the Ethylene method. By references versus order parameter by BM062X method. The M062X method does not have any sharp edge, but the B3 method has a sharp. The 701, 702, 703, and 74 have the same order parameter. After the 704, the order parameter fluctuates with the Y references. The order parameter and Y references of 706 Fc molecules sharply decreases because the bond orientational order breaks rotational symmetry and exhibit symmetric F phase. Even odd effect of homogenization NCHBT liquid crystal molecule under the influence of electric field. Transition temperature. Experimentally reported the increase of amount of melting point observed when the number of carbon atom alkyl chain is odd and small changes in rigid core structure lead to the change in attractive and repulsive forces. The transition temperature expresses the even-odd effect under the extension of alkyl chain length of NCB steam liquid crystal. The odd carbon number has a higher perspective, however the even carbon number has the lower perspective. The dipole moment. The even carbon number of alkyl chain expresses higher value of dipole moment, while the odd carbon atom expresses lower value of because the CH bagging and CH twisting frequency increases for even carbon atom number of the Benzene ring, but the twisting frequency decreases for odd carbon atom. The CH stretching frequency is also responsible for even carbon atom in the upward direction and odd carbon atom in downward direction. The variation of dipole moment indicate the CH-BT-LC molecule are changing shape and size due to increase in the alkyl. The 9-HBT shows the refractive index sharply increased because the IR absorption found to be very high in 9-HBT-LC by the cause of the CH wagging frequency of benzene ring. The rocking frequency correspond to IR absorption has found to be very high in the tail of 9-CBT. The CN stretching correspond to IR absorption is continual increases with the CBT series, but the CN stretching decreases the NCBT LC battery region for enhanced effective index. Birefringence. Experimentally reported birefringence decreases with the extension of alkyl chain. In the present work also birefringence decreases and expresses even odd effect due to an increment of alkyl chain length because the CS symmetric and asymmetric stretching correspond to IR absorption increases for the odd carbon number and decreases with even carbon atom number of benzene and cyclohexane ring. Order parameter. The order parameter continuously increases with the increment of alkyl chain length because Cn and Cc atom stretching correspond to the IR absorption continuously and decreases for the NCVT series. The order parameter has expressed an even odd effect with minor deviation. This is the representation of order parameter in 3 dimensions. Magic angle. The magic angle decreases continually with the increased alkyl chain, but the magic angle increased again in 10 CVT. However, NCVT maintain 54.7 magic angle for all series. The magic angle of liquid crystal molecule depends upon the molecular anisotropy. The NCVT liquid crystal series have uniaxial, however, the 9-CHBT is biaxial. The magnetic angle of 9-CHBT decreases and 10 CHBT increases due to uniaxial behavior of the liquid crystal. Range of director angle. The range of director angle continually increases with extension of alkyl chain. The Cc and Cn atomic stretching contribute to the enhancement of frequency due to the range of director angle increases continually. The maximum director angle continually decreases with the extension of alkyl chain length. The maximum director angle remains constant 55 degrees because the CH bond stretching of benzene ring remains constant for all series. Isotopic polarizability. Experimentally reported pi-electron conjugation of phenyl ring with the terminal NCH group gives strong polarizability as comparison with the CN group. The isotopic polarizability increases continually with alkyl chain length because CN atom stretching corresponds to higher absorption continuously increases as well as CH twisting frequency of the benzene continuously increases. The strategy of the present review can predict the physical parameter, dipole moment density of state, isotopic polarizability, intermolecular interaction of unknown. The motivation of this work is to search for new liquid crystals which are suitable under the terahertz application. The DFT method exhibits perfectly electro-optic odd-even effect under the applied electric field calculated by given equations. With the help of the methodology, we can predict the optical and sensing property of unknown organic molecule. Molecular polarizability is the most crucial parameter in this work, which is responsible for the optical properties and the organic molecule. These are the acknowledgements. Thank you for your time.